Good evening, ma'am. I'm Tejaswini from CSO. So my today's seminar topic is magnetism, and the subtopics I'm going to talk about are magnet properties, magnetization, origin of magnetic moment, dipole moment, classification of magnetism, and the hysteresis graph, that is also called as pH graph, and hard-soft magnets differences. So firstly, what is magnetism? The force of attraction or repulsion of a magnetic material due to the arrangement of its atoms, particularly its electrons, is nothing but magnetism. So, as you can see clearly, the magnet contains two poles, it is north and south, and its attraction or repulsion with other magnets or other magnetic substances is nothing but magnetism. So, on the side note, what is magnetic flux? Magnetic flux can be defined as a measure of magnetic field in a certain medium. In simple terms, the magnetic field had to pass through a certain medium. It will always travel as flux lines. There is these lines between this line between this north and south poles. There is these lines of attraction or nothing but the flux lines. That is the magnetic flux. And the units of this magnetic flux are Weber. So, uh, now Now that we know the definition of what is magnetism, let's see what are magnets and non-magnets. Clearly, the substance which attracts iron, steel, nickel, and cobalt is called magnet, while the substances which do not attract, that is, other magnetic substances like iron, steel, nickel, and cobalt, are called non-magnets. Now, let's see them clearly in this PPT examples. See, these all are there is a nickel knife or something made of copper or steel, iron, or are examples of magnetic materials, for other remaining materials like wood or paper, which are not at all attracted to these substances, are non-magnetic materials. Now, what is magnetization? Conversion of these non-magnets into magnets, which is nothing but magnetization. While the demagnetization is on the contrary of it, there's conversion of magnets into non-magnets. So, on the basis of the nature, the magnets are divided into four types: it is natural, artificial, temporary, and permanent. Now, let's see them in detail. So, what are natural magnets? Those which are naturally found in the ground, that is, on the earth, easily, in rocks, that is, in iron ores and magnetite ores, lodestone, and which are available naturally in our environment, are nothing but natural magnets. Whereas temporary magnets are which are made into magnets temporarily by striking with permanent magnets. That is, by striking a soft iron object with a permanent magnet, it becomes a weak magnet even though it's temporary. Now, let's see how we can see these temporary magnets and permanent magnets in general. Temporary magnets are those which act like a permanent magnet when they are within a strong magnetic field, but lose their magnetism with the magnetic field disappears. Examples would be paper clips and nails and other soft iron items, as you can clearly see in this figure, as we discussed before. And permanent magnets are those which we are familiar with because they are the magnets hanging onto refrigerator doors. These are permanent in sense that once they are magnetized, they retain a level of magnetism. Now, to summarize, we can say that natural magnets are nothing but magnets available originally in our universe. That is, Earth itself, the planet Earth which we live on, is in and itself is a magnet. And artificial magnets are magnets prepared artificially by man, and they can be again further divided into three types, that is, bar magnets, disc shaped magnets, and horseshoe magnets. And while temporary magnets, these are the magnets which lose magnetism with uh, external conditions, while permanent magnets which will never lose magnetism with any kind of external conditions. So now let's discuss the main properties of magnetism. One is the dipole. What is dipole? Dipole is nothing but a magnet is a dipole with two poles, that is north pole and south pole. Pole strength. Strength of each pole in a magnet, that is strength of the north pole and south pole. Magnetic moment. This is the product of pole strength and magnetic length, that is 2L. So capital M, that is magnetic moment, equals to M into 2L. And magnetic length, this is the distance between two poles in a bar magnet, which we discussed just now. Geometric length is the distance between the edges of the bar magnet. There is if this is the distance and from this point to this point is the distance between the magnet, is can be called as magnetic length. This whole length is called as geometric length. That is between the distance between two edges is geometric length, while between these two poles is magnetic length. And magnetic flux, it is, as we discussed before, group of magnetic force lines transmitting from north pole to south pole. That is, these lines are nothing but flux lines. And magnetic flux density, that is the total magnetic flux passing from north pole to south pole of a bar magnet. That is, this total amount of flux is nothing but magnetic flux density. And magnetic field, the region or space around the magnet until which its influence exists. That is up to how far these flux lines extend is nothing but magnetic field. Permeability, the ability of a medium to permit magnetic flux lines. There is some mediums may allow or some may not allow. So up to how much amount of flux the medium can accept is nothing but the permeability. Now this permeability can be represented in three ways. That is mu, that is medium permeability, mu naught, vacuum or free space permeability, and mu r is the relative permeability between medium permeability and vacuum permeability. That is mu r by mu naught. And susceptibility, it is nothing but the ratio of magnetization and applied magnetic field is equals to m by h. Now the relation between VHM, there is nothing but the relationship between magnetic flux density, magnetic field, and magnetic moment can be written as, for medium, B is directly proportional to H. That is, magnetic flux density is directly proportional to the magnetic field present. So removing the this proportionality, we'll write B equals to mu H, where mu is nothing but permeability. While for free space, that is for vacuum, B is proportional to H plus m. That is, in vacuum, we'll also consider the magnetization due to this extra magnetic moment. So we'll write it as B proportional to H plus m. That is, B equals to mu naught. That is permeability in vacuum or free space into H plus m. Now the other common property we all know that is magnets can pass through solids and gas and liquids. That is, they can pass through anything because flux lines can pass through anything, even in vacuum too. Now let's discuss the relationship between mu, that is relative permeability and susceptibility. So as we written before, in medium B equals to mu H, and mu R is equals to, that is relative permeability is equals to mu in medium by mu of vacuum. This equals to mu can be written as mu naught into mu R. Substituting this mu value here, B equals to mu naught mu R H, and from this we can write that mu naught mu R H plus mu naught H minus mu naught H. That is, we are just adding and subtracting this term mu naught H, and taking this common, mu naught H into mu R plus 1 minus mu naught H. And from this we can generalize this formula as susceptibility is equals to mu R plus 1 for weak magnets. That is, for demagnetization, the susceptibility for weak magnets is mu R plus 1, whereas for strong magnets, for the susceptibility formula for magnetization is mu R minus 1. These are some two important general formulas for weak magnets and strong magnets and their respective demagnetization and magnetization. Now coming to the next topic, magnetic domain. A domain, what is a domain? A domain is nothing but the ferromagnetic materials or any magnetic materials in general are divided into many regions, and this region, each region is nothing but called as a domain. So iron and other ferromagnetic substances are though a bit different. Their atomic makeup is kind of a bit similar. That is, they have same magnetic orientation. That is, instead of each of these domains, the electrons are oriented in the same direction. But it's not the case in iron when there is no external magnetic field. But on the application of external magnetic field, all these magnetic dipoles, that is magnetic moments, will get will move from a random positions to a straight alignment. Now we already just discussed domain. What we have to note here is domain theory was proposed by the scientist called Weiss. Now if we have to talk about dimensions of each of these domains, that is each of these various regions of the magnetic material is 10 power minus 6 meters, and each domain has its own directions, own orientations of magnetic dipoles. So while as we discussed before, on the application of external magnetic field, all these dipoles are set in a straight line motion from their random motions. But we have to note that on very application of very strong magnetic fields, these lines, instead of going straight lines, they keeps moving in rotations. So we can say that domain wall, that is these lines, these dipole moments, domain wall movement happens with the application of magnetic field, while domain wall rotation, as we seen here, happens with the application of very strong magnetic field. Now let's discuss about types of magnetism. So magnetism is of 5 types, and the first 3 types, ferromagnetism, and paramagnetism, they possess net magnetization. That is, they can be magnetized somehow, but it's not the case in the last 2 types. There is diamagnetism and antiferromagnetism, as we can see here. Now, let's talk about these 5 magnetisms in detail by comparing with them with each other and their several properties. Now, the first property is whether the atom dipoles are permanent dipoles, that is nothing but these magnetic moment lines, which were seen just now in all these cases in their respective domains. So, nothing but the atomic dipoles. So, as we can see, in diamagnetic materials, there is no dipoles present at all before magnetization, but in all other types of magnetic materials, these dipoles are present, and this is clearly the representation of these magnetic dipoles. But after magnetization, even in diamagnetic materials, they gain dipole moments, even though if they are not present before application of magnetic field. While in paramagnetic materials, before applying field, these dipole moments are in very random motion, but on the application of field, they are set into a straight line motion. While in ferromagnetic materials, before they are in a straight line motion, but after magnetization, what happens is these magnetic uh, poles are literally obliterated. There are no magnetic poles remaining after the application of magnetic field in ferromagnetic materials case. While in antiferromagnetic materials case, before they are random and after on the application of the magnetic field, external magnetic field, they are uh, formed as pairs of magnetic moments. That is, each pair that is a clockwise spin and an anti-clockwise spin. It's also the same case in these two, also we have to note that in these antiferromagnetic materials, these two, since these are opposite spins placed side by side, they get cancelled each other, so no exchange coupling. While in ferromagnetic materials, these spins also are in opposite directions, but what is happens here is they do not get cancelled. That is, they are of different magnitudes. Another notable points are there is no spontaneous magnetization in this diamagnetic materials, and also there is no exchange coupling as we discussed before. And in paramagnetic materials, no spontaneous and magnetization and no exchange coupling too. While in ferromagnetic materials, there is a spontaneous demagnetization, and also exchange coupling also exists. In antiferromagnetic materials, there are also no exchange coupling and no spontaneous magnetization, which is also the similar case in ferromagnetic materials. Now, this can be summed up as on the application of magnetic field, the ferromagnetic in the ferromagnetic materials, magnets, magnetic moments are aligned. In antiferromagnetic materials, zero net magnetic moment at sufficiently low temperatures, while because these two, since they are in the opposite spins, they get cancel each other. While in ferromagnetic materials, magnetic moments oppose, but they do not cancel because we can clearly see here these are of different magnitudes. And while in paramagnetic materials, random magnetic moments occurs. Um, while with magnetic moments will align with the application of magnetic field as we've seen before. Now talking about other properties, the magnetic nature for diamagnetic materials it is weak. For paramagnetic materials it's partially strong or partially weak. For ferromagnetic materials it is very strong, and for antiferromagnetic materials it is strong, and also for finally for ferrimagnetic materials also it is strong. And it's the same case for magnetic field nature too. Now, if we talk about how these magnets acts on the application of external flux, uh, these diagrams represents them very clearly. On the application of external magnetic flux, these diamagnetic materials, what they'll do is they'll simply let them pass through, but not through them, but in through their surroundings. While for paramagnetic materials, they will let these out external magnetic flux lines pass through them. That is, they are they let them get partially attracted to them, while the non-magnetic materials will just completely straight up repel them. Now this ferromagnetic materials let them completely pass through them, so they are very strongly attracted to the external magnetic field. And while antiferromagnetic substances, they also let them pass through them, but not as much as that of ferromagnetic substances. So they are not very strongly attracted, but strongly attracted, which is also the same case in the last one, ferromagnetic materials. And if we talk about the susceptibility for uh, diamagnetic materials, it is negative and small. For para, it is positive and small. For ferro, it is positive and large. And for antiferro, it is positive and small. And for ferromagnets, it is positive and large. And we can uh, say magnetization is similar to that too, because susceptibility is proportional to magnetization. So it will be the same case here. That is, M is here 0, low, high, 0, high. Now, if we see the effect of temperature on these different types of magnetized materials, for paramagnets, the graph can be stated as susceptibility is proportional to 1 by T, that is susceptibility equals C by T, where C is nothing but Curie constant, and it's a slight hyperbola type graph. And for ferromagnets up to the point Tc, that is the Curie temperature, it acts as a ferromagnet itself, but after the further application of temperature above Curie temperature, it acts as a paramagnet. And for antiferro, before this N, T, and there is nil temperature, it acts as antiferromagnet itself, but after, when the temperature is further increased than the nil temperature, it becomes para. While for ferrites, that is nothing but ferrimagnetic substances, before the Tn, there is nil temperature, they remain as ferrites, they retain their properties, but after further application of temperature greater than Tn, they become paramagnets. And their equation can be written in this order. So for the some examples of these different magnetized substances are diamagnetic materials are superconductors. For para, they are alkali and transition materials. And for ferromagnets, they are iron, steel, nickel, and cobalt. For antiferromagnets, they are oxides, alloys, and MnO, and a few, that is manganese oxide and ferrous oxide. And for ferromagnetic materials, they are simply ferrites, are some of the examples of these different types of magnetized materials. Now that's all about the properties and the comparisons between these different types of magnetized materials. Now, coming to the next topic, there is hysteresis curve of or pH curve, which shows the behavior of magnetic materials on increasing the flux and how much they are getting magnetized. It is how much magnetic flux or density is passing through them and they are responding to it. Here in this graph, we can clearly see that different 4 stages from 0 to H max, that is from 0 to H max. Clearly see that it's reaching the saturation point of magnetization, that is the magnet is positively highly magnetized at this point. This is the highest point it can reach for its magnetization. And from point H max to 0, that is from this to this, that is the AC curve, up to the point B, this point can be taken as positive retentivity. Now what is retentivity? Regentivity is nothing but the phenomena of having magnetism even though applied magnetic field H is 0. So, as we can clearly see that at this point B, there is no external magnetic field. That is, X is clearly 0, even though it is having some magnetism in it. So, this point is positive retentivity, while this point E, which we'll later discuss, is negative retentivity. That is, and after passing through this point P of positive retentivity, after reaching this point C, it shows negative coercivity. Now what is coercivity? Coercivity is nothing but the phenomenon of having magnetism even though the field is applied in the opposite direction. That is, even the external field is shown in the negative direction of it, it is showing the property of magnetism, and this point is called, thus we call this point as negative coercivity. And after passing through this point, it is straight up reaching from 0 to minus h max, that is from 0 to this point it is reaching the point of negative saturation of magnetization. That is, this is the point where it is magnetized to a higher extent but with negative magnitude. And from this point, once again, it reaches the point 0, passing to the point E, which we discussed before, is exhibiting negative rotativity because clearly, even though the external magnetic field which is applied to the certain magnet is 0, it is showing magnetism, but this magnetism is of negative magnitude, so we'll call this as negative rotativity point. And after this, once again, it passes to a positive coercivity point, which is the opposite of negative coercivity point in terms of magnitude. And once again, it reaches the initial point A, that is through this dA curve from 0 to positive H max. Thus, these are the properties and how the magnet acts with different on different applications of magnetic field magnitude, and how it gets magnetized at each and every point, showing different properties like properties of it like coercivity and rotativity. Now, the next topic is the differences between soft and hard magnetic materials. Soft magnetic materials are nothing but those materials which have low retentivity and low coercivity and small hysteresis loss and high saturation magnetization, while hard magnetic materials are nothing but the materials which high retentivity, high coercivity, low hysteresis loss and high saturation magnetization. That is, uh, these soft magnetic materials are easy to be magnetized because we can see this width is very less compared to this hard magnetic materials. This width is less means we only require less external magnetic field to make these materials magnetize. While the hard magnetic materials, this width is broad, which indicates that more amount of magnetic field, external magnetic field is required to magnetize these materials. So it is difficult to magnetize them. Also, we can say that these soft magnetic materials are suitable for temporary magnetism, while these are hard magnetic materials are suitable for permanent magnetism. Let's see for the differences. For soft magnets, the hysteresis area is low, which was seen before. The width right here is very low, while for hard magnetic materials, it's very high. And the magnetization here is easy and is difficult as we discussed before. So similarly, the case for demagnetization also will be the same, easy, difficult. And retentivity, it's in itself, the retentivity and coercivity both are low for soft magnetic materials, and retentivity and coercivity are both high for hard magnetic materials. And similarly, susceptibility is high. What is susceptibility, which we discussed before? It's nothing but it's similar to magnetization, right? It is proportional to magnetization. So since these materials, these magnetic materials are easily magnetized, their susceptibility is high, while it is low for hard magnetic materials. And related to permeability is also similar, it's high for soft and low for hard. And these applications which we discussed before, temporary magnets for soft magnetic materials and permanent magnets for hard magnetic materials. Now coming to the final and important topic, that is origin of magnetism in materials. Now, in every atom, there exist three different types of spin, and the main three types of spins, that is the nuclear spin of the atoms and the spin of the electrons and orbital motion of the electrons, gives us magnetism. These are the origins of magnetism right here. But the what in terms of magnitude they may be different. That is, nuclear spin gives a peak effect, while spin of electrons, that is n-pair electrons required for the net magnetic moment in this case, while for orbital motion of electrons, this effect is very strong compared to the nuclear spin. Now let's see them in detail. That is origin law of magnetic moment, that is magnetism. Now, as we discussed, every atom magnetized with these three types of magnetic moments. That is, these magnetic moments are nothing but due to the spin of this particular nuclear spin or spin of electrons and orbital motion of electrons, which can be divided into three types. That is mu naught, orbital magnetic moment; mu s, spin magnetic moment; and mu n, nuclear magnetic moment. Now, the first one is orbital magnetic moment, mu naught. Now, let's derive the formula for this orbital magnetic moment. Now, in general, we know that I, that is electric current, is nothing but rate of change of charge is equals to Q by T. So where q is equals to minus c, that is charge, electronic charge, and t equals to time. And this, if you write the term in terms of angular velocity and angular displacement, t equals to 2 pi by omega, and substituting this value in I, we get that I equals to e omega minus e omega by 2 pi. Now taking this as equation 1 and keeping it aside, we know that magnetic moment is represented by I into A equals to mu. And A is nothing but area, I is equals to current, and mu equals to magnetic moment. So mu equals to, substituting these values, A for pi r square and I for E minus E omega by 2 pi, we obtain that magnetic moment mu equals to minus E by 2 m into m r square omega. Now we know that angular momentum L equals to I omega, where omega is equals to angular velocity and I equals to moment of inertia. And we know that formula for moment of inertia, which is nothing but mr square, where m is equals to represents mass and r represents radius. So L equals to I omega, where I equals to mr square, so L is equals to mr square omega, and we substitute this, replace this mr square omega value for this magnetic moment with L. So mu is nothing but E minus EL by 2m, and further replacing the value of L, which is also nh by 2 pi here, we finally obtain that for orbital magnetic, there is here n represent nothing but the number of orbitals. So for orbital, magnetic moment can be represented as minus n into eh by 4 pi m, which can also be written as minus n e mu b, where mu b is a universal constant, which is also called as Bohr magneton, whose value is h by 4 pi m, that is 9.27 into 10 power minus 24 Armstrong meter square. In the similar way, we can also obtain the equation for spin magnetic moment, like how we did for the orbital magnetic moment. We can obtain the equation for mu s equals to minus half into eh by 4 pi m, and for nuclear magnetic moment it is eh by 4 pi mp. So this will be the value for the nuclear magnetic moment, which is common for every nuclei. So these three are the major contributors, that is the origins of the magnetic moment. So these are all the major topics which we are thought to discuss in this magnetism seminar. They are completed. So thank you.